What happens when an interviewer wants to truly test your algorithmic efficiency? Merge case sorted lists is a pattern mastery 100 heavyweight and a frequent guest at Google, Amazon, and Microsoft interviews. Over 40% of candidates get slowed down by the complexity and pointer management. Master this, and you'll prove you can handle multi-list merges, priority queues, and advanced patterns.
Let's attack merge case sorted lists with the basic problem-solving framework, a stepwise guide for turning chaos into clarity, even in the toughest coding rounds. Let's break it down. Given an array of k-linked lists, each sorted in ascending order, merge them all into one sorted linked list and return its head. Example: input 145, 134, 26. Output 1, 1, 2, 3, 4, 4, 5, 6. Real-world example: think about a system that needs to combine multiple log files, each sorted by timestamp, into a single unified log for analysis. A classic interview extension. How would you merge sorted streams from different servers in real time? Let's assess it. What's tricky here? Naive approach. Merge the lists one by one using the two-list merge logic, O-kilonewton, time, where n is total nodes, works, but not optimal. Optimal approach. Use a min-heap, priority queue, to always pick the smallest head among the k-lists, giving you O(n) log k time. Let's think step by step. Push the first node of each list into a min-heap, keyed by node value. Repeatedly pop the smallest node from the heap, attach it to the merged list, and if there's a next node in that list, push it into the heap. Continue until the heap is empty. Let's dig deeper. Why a heap? It guarantees that at each step, you can efficiently, in O log k, get the smallest remaining node across all lists. Using a dummy node for the result list keeps the code clean and bug-free. Edge cases? Some lists may be empty. All lists empty? Output should be null. Here's the structure. Create a dummy head for the result list and a current pointer. Initialize a min heap and insert the first node of each list if not null. While the heap isn't empty, pop the node with the smallest value. Attach it to the current pointer. If the pop node has a next, push that next node into the heap. Move current forward. Return dummy.next. Now, let's look at the idea behind this solution. We are merging two sorted lists iteratively. We start by looking at the first nodes of both lists. We pick the smaller one and attach it to our new merged list. Then we move forward in that list. We keep repeating this process until one list finishes. Finally, we attach whatever is left from the other list. It's just like merging two sorted lines of people into one line, always picking whoever has the smaller number first. We start by creating a dummy node, which is a simple placeholder that helps us build the merged list without worrying about special cases. Next, we create a tail pointer to keep track of the end of our merged list. Right now, the dummy node is the end. We now start a loop that runs as long as both lists still have nodes. It's like comparing two people at the front of two lines. Inside the loop, we check which list has the smaller value at the front. If the first list has the smaller value, we attach that node to the merged list. Then we move forward in the first list, just like sending the next person to the front of the line. Otherwise, the node from the second list is smaller. We attach the node from the second list instead. Then we move forward in the second list. No matter which list we took from, our merged list has grown. So we move the tail pointer to the newly added node. After the loop ends, one list might still have remaining nodes. We simply attach that entire leftover section to the end. No more comparisons are needed. Finally, we return dummy.next because that is the real start of our merged list. The dummy node was only a helper. So, to summarize, this algorithm first sets up a helper node to simplify building the new list. Then it repeatedly picks the smaller value from the two lists until one runs out. Finally, it attaches any remaining nodes from the other list. It is efficient, simple, and elegant. Only one pass through both lists is needed, so the total cost is OM plus N. The dummy node avoids tricky edge cases. Merging works cleanly because both lists are already sorted. We start with two sorted linked lists. The first list contains the values 1, 2, and 4. The second list contains the values 1, 3, and 4. Our goal is to merge these two lists into a single sorted list. As we compare nodes from both lists, we always pick the smaller value and move forward. Both lists begin with the value 1, so we add 1 first. Next, we compare 2 and 3, and select 2. Then we select 3, followed by 4 from the first list, and finally 4 from the second list. The merged result is 1, 1, 2, 3, 4, 4. The output matches the expected result, so the test case is accepted. The time complexity of this algorithm is OM plus N, because we visit each node in both lists exactly once. Here, M is the number of nodes in the first list, and N is the number of nodes in the second list. Now, let's look at the idea behind this solution. We are merging two sorted lists recursively. We start by comparing the first nodes of both lists. We pick the smaller one and attach the result of merging the rest recursively. We repeat this process until one of the lists is empty. It's like asking, who's smaller? Let's take them. Then do the same for the remaining people. If the first list is empty, we simply return the second list. There's nothing to merge from the first list. Similarly, if the second list is empty, we return the first list. Next, we compare the current node's values. If the first list's value is smaller, we attach that node first. Then comes the recursive magic. We set the first nodes next to the result of merging the rest of the first list with the second list. Think of it as saying, I picked this node, now merge the rest. After linking, we return this node as the new head of the merged part. If the second list value is smaller or equal, we do the same process for the second list. We attach the result of merging the first list with the rest of the second list. We always move forward recursively. Finally, we return this node as the head of the merged part. So, to summarize, this recursive algorithm first checks for empty lists. Then it repeatedly picks the smaller node from the front, attaching the merged rest recursively. It is elegant, concise, and efficient. Only one pass through both lists is needed, so the total cost is OM plus N. Recursive calls handle merging automatically. It works cleanly because both lists are already sorted.
For solution 2, we use the same test case and follow the same comparison steps. Since the inputs and logic are unchanged, the merged result is exactly the same. The output matches the expected result, so the test case is accepted.
Breakdown recap. We're given an array of k-sorted linked lists and need to merge them all into one fully sorted linked list. Conceptually, it's about combining multiple sorted sequences into a single unified list. Assess recap. A naive approach would merge the lists one by one using two-list logic, but that's slow. The optimal approach leverages a min-heap, priority queue, to always select the smallest node across all lists. This reduces the complexity significantly and makes it efficient even for many lists. Structure recap. Here's the plan. Create a dummy head for the merged list and a current pointer. Initialize a min-heap and push the first node of each list, if not null. While the heap isn't empty, pop the smallest node, attach it to the merged list, and if that node has a next, push it into the heap. Move the current pointer forward and continue. At the end, return the merged list. Implement recap. We implemented this using a min-heap, storing tuples of node value, node, to ensure proper ordering. Running it on LeetCode, the solution executed cleanly and efficiently merged all lists without errors. Check recap. We verified the logic across all general cases and edge cases. The solution runs in on log k, time with OK space for the heap and produces correct results consistently. Closing insight. The key takeaway? When merging multiple sorted sequences, a min-heap is the most effective tool. It lets you efficiently track and select the smallest current element, keeping the process clean, fast, and scalable for any number of lists.